But some desert ants do the exact opposite. They burst from their nests to forage during the hottest part of the day. This is Death Valley. It's famous for holding the world record for the highest air temperature ever reliably recorded on our planet. The official record here hit 56.7 degrees Celsius, or 134 degrees Fahrenheit, back in 1913. The ground itself can get much hotter, soaring to temperatures that would cook most living things instantly. It's a beautiful, brutal place, and seemingly impossible for life to exist. And yet, life is here. Down on that scorching sand, where the heat is at its most punishing, a tiny creature doesn't just survive, it thrives. This isn't a story about just enduring the heat, weapon, into its own personal advantage. This is the story of how desert ants reverse-engineered death itself. To get the genius of the desert ant, you first have to respect the enemy, heat. In deserts like Death Valley or the Sahara, heat is a two-pronged attack. First, there's the relentless, direct radiation from the sun. Second, and even more dangerous, is the heat blasting back up from the superheated ground. For a creature just millimeters tall, the sand is a frying pan. Most animals run from it. They hide underground, or only come out at night. But some desert ants do the exact opposite. They burst from their nests to forage during the hottest part of the day. And there's a very good reason for this apparent madness. At peak heat, their predators, like lizards, are forced into hiding. At the same time, the desert floor becomes littered with the unfortunate, other insects and arthropods of opportunity. A brief, all-you-can-eat buffet in the deadliest restaurant on Earth. But this window is terrifyingly small. The ants can only survive these temperatures for a matter of minutes. Every second they're outside the nest, a clock is ticking. Stay out too long, and they become just another casualty for a different scavenger. To pull off this daily heist, they need a whole toolkit of biological hacks. To see these in their most extreme form, we need to look at a true champion of the desert, the Saharan silver ant. While its specific strategies aren't universal for all desert ants, when you first see a Saharan silver ant, it looks like a drop of mercury skittering across the sand. That shimmering, metallic glint isn't just for show. It's the first of its survival hacks, a remarkable coat of hairs. Under a microscope, these hairs are revealed to have a unique triangular cross-section. This precise shape lets them work in two ways at once. First, the hairs are brilliant at reflecting visible and near-infrared light, the wavelengths that carry most of the sun's energy. Like a tiny, wearable space blanket, this silvery coat bounces solar radiation away from the ant's body, keeping it significantly cooler. But that's only half the trick. While the hairs reflect sunlight, they're also incredibly good at helping the ant shed its own body heat. In the mid-infrared spectrum, the wavelength of thermal radiation, the hairs enhance the ant's ability to radiate its internal heat away into the much cooler sky. It's a passive cooling system, a biological radiator that helps the ant offload the heat it generates just from moving. This thermal armor is crucial, but it only solves the problem of heat from above. What about the blistering heat coming off the sand? The answer is simple yet brilliant. Get away from it. Desert ants have noticeably longer legs compared to other ants. These aren't just for running fast. They're stilts. By lifting its body just a few extra millimeters off the ground, the ant puts itself in a cooler layer of air. The temperature difference just above the desert floor is huge. A few millimeters of height can mean a significant drop in temperature, giving it a vital buffer against being cooked from below. With its armor and stilts, the ant is ready for the heist. The nest opens, and the foragers burst out. Their movements are frantic, efficient, and unbelievably fast. The Saharan silver ant is the fastest ant clocked at breathtaking speeds of 855 millimeters per second. To put that in perspective, it covers 108 times its own body length in a single second. A feat that, relative to size, would be like a human sprinting at over 700 kilometers per hour. This speed isn't for show. It's about minimizing time. Every fraction of a second on the sand pushes it closer to its thermal limit. Speed is life. They sprint across the sand. They search for food in a zigzag pattern. When a forager finds a prize, the next great challenge begins. It now has to get this food back before its internal clock runs out. It's incredible how evolution has engineered these multi-layered solutions for a single problem, the bell icon. We dive into the amazing engineering of the natural world every week. In the searing heat of the desert, many of the navigational tools other ants rely on are useless. Chemical pheromone trails would evaporate almost instantly on the hot sand. And in a landscape of shifting dunes, visual landmarks can be scarce. So how does the desert ant find its way home? It uses one of the most sophisticated navigation systems in the animal kingdom, path integration. Think of it as a biological geese that needs no satellites. It works by constantly tracking. For direction, the ant has a built-in celestial compass. Its specialized eyes can detect patterns of polarized light in the sky, which are invisible to us. This pattern is directly related to the sun's position, giving the ant a constant and reliable directional cue. As it runs, its brain monitors how its body is angled. For distance, the ant uses an internal odometer, essentially a stride integrator. For a long time, scientists were baffled by this. The answer was discovered through a beautifully simple experiment. Researchers let ants run from their nest to a food source. On the way back, they captured some of them. One group had tiny stilts glued to their legs, making them longer. Another group had their legs shortened. The ants with stilts, now taking longer strides, overshot the nest. The ants with shortened legs, taking smaller strides, stopped short. This proved the ants gauge distance by integrating their stride length and number. So, on its chaotic, zigzagging outbound journey, the ants constantly logging every turn, every step. Even with all these external defenses, the heat inevitably takes a toll. The ant's internal body temperature can climb to a critical point where the proteins that keep danger of breaking down. This is where the final, and perhaps most critical adaptation comes in, a defense system at the molecular level. Many organisms have something called heat shock proteins, or HSPs. You can think of them as a cell's emergency response team. When a cell gets too hot and its proteins start to misfold, HSPs rush in to refold them, protect them from damage, and keep the cellular machinery from failing. But in the desert ant's world, there's no time to wait for the fire alarm. The temperature spikes too fast. If they waited until they were already overheating to start making these proteins, it would be too late. So, research shows that highly heat-tolerant ants like Cataglyphus come prepared. They have elevated baseline levels of these protective proteins before they even leave the nest. This pre-adaptation gives. So, research shows that highly heat-tolerant ants like Cataglyphus come prepared. They have elevated baseline levels of these protective proteins before they even leave the nest. This pre-adaptation gives. It sprints on long, stilt-like legs, keeping its body just above the hottest layer of air. As it zigzags, its brain constantly updates an internal map, using the sky's polarized light for direction and its own stride count for distance. Deep within its cells, an army of heat shock proteins is already on standby, holding the line against thermal collapse. It finds its prize. Instantly, its internal GPS calculates the shortest path home. There's no hesitation. It turns and sprints in a dead straight line, dragging its cargo. It arrives at the tiny, inconspicuous opening of its nest and vanishes underground into the cool darkness, just as its body was reaching its absolute thermal limit. This tiny creature hasn't just learned to live, it has evolved thermal armor. Through millions of years of evolution, the desert ant has done more than just adapt. It has, in its own way,